So I'm going to talk about joint work with Thomas van Beek, which is my student, Ravishankar Ramanathan, which is a postdoc in Brussels and was previously with the Oretsky, Jonathan Borbrask, which is in Geneva, but will be going back to Copenhagen this year, and Annabelle Henson and Ellie Wolf at the Perimeter Institute. So what we have been trying to do is trying to understand when a general device independent scenario exhibits a quantum advantage. And what I mean by a device independent scenario is something like the Bell scenario, or the standard Bell scenario. So you have two quantum devices, which you view as black boxes. They get some classical inputs, produce classical outputs, and these two boxes can share entanglement. So maybe sometime in the past, there was a quantum source which sent quantum particles to these two devices. And more generally, you could have many such quantum devices with many quantum sources, and maybe these devices are used in some complicated sequence. And what you observe is the classical data, and so you have a probability distribution over this classical data, and then you would like to know whether it admits a classical or a quantum representation. And so, so you're trying to understand that. So this is really work in progress. So I don't have many results to present, and most of them are half-baked, but at least I can tell you a little bit about the questions that we are looking. And actually, we've been considering this problem from the complementary perspective, so trying to find situations where there is no quantum advantage, and even no advantage within a general probabilistic theory. So like even if you had Pierre boxes or stuff like that. Okay, and maybe by understanding when there is no quantum advantage, we learn about something also about when there is one. And the side product of this kind of approach is that by discarding all device independent scenarios which are boring, in the sense where there is no quantum advantage, you can identify also the simplest device independent scenario where there is a quantum advantage. And so I will say a few words about this. And this is not the standard Bell scenario, actually, but it's closely connected to it. OK, so this is the standard Bell scenario. So here we have a device that outputs a variable. So this is a random number generator. The same thing here. So this random variable goes into some other device. This device also can receive some systems coming from a source, and then it produces some classical data here, A, and we have the same thing there. And we treat everything like black boxes, so we are only interested in the classical data, which is characterized by some joint probability distribution. And then you can define sets of probability distribution which admit a classical quantum or a causal generalized probabilistic description. So these are I call CQG. And as you know, they are all distinct. So we have Bell inequalities, which are satisfied in the classical set but violated by quantum theory. We have Cyrolson inequalities in quantum set, which can be violated by Pierre boxes. So it's possible to distinguish whether an experiment belongs to one of these sets only by looking at the probability distribution of the observed data. So this is a device-independent statement. We can say something about the underlying physical system by looking only at the data it produces. And this is a very basic statement. You can say that, OK, this setting doesn't admit a classical description. But as you know, one can also make more refined device-independent statements, like one could certify that a certain amount of randomness has been produced, or you could self-test the states of the measurements, and then this could be used maybe in device-independent protocols, like for self-testing quantum computers. But the starting point, of course, it's you always want to have this separation, because if everything can be described classically, you will not have all this self-testing property. So this is this basic property that we are interested in our project. So of course, I can generalize this. I can have many parties, like here three measuring stations, and a source of tripartite entangled states. I can also consider a situation where instead of having one source of tripartite entangled states, I have two independent sources. So this is what you would have in a typical entanglement swapping experiment. So here at B, there is a joint measurement that's performed on 2 incoming quantum states. And if you take into account the fact that you have 2 independent sources, you can come up with experimental tests of non-classicality, which are more refined than if you treat everything as just one source. So it's easier to demonstrate non-classicality in experiment if you take into account this independence condition here. You can, of course, have not 2 sources, but many. So you can have non-locality. So here in a chain. So this is the kind of configuration we'll have in a quantum repeater experiment. Interestingly, when you have 3 independent sources like that or more, you don't need to have random choices for the measurements. So you can have a situation where the measurements are fixed, and yet the data that you produce cannot be explained classically. You can have unlocality with different configuration, like here a star with 3 branches. This is an interesting situation. It's called triangle scenario. So it seems very simple, but it's very difficult to characterize. Even in the classical case, we don't know what are the constraints that are satisfied by this probability distribution in the general case. Even in the simplest case, actually, where A, B, and C are binary. We can also consider more complicated stuff like this hidden locality introduced by Popescu in 1995, where here you have a source, and then which sends quantum systems, and then here you perform some measurements depending on some random settings. So there is an outcome, but there is also a quantum system going out, which can be measured in a second step. Okay? So you can have sequence of measurements, and in all these scenarios I presented, there is always a separation between classical and the quantum case. Okay, so we could go on, introduce zoology of this kind of networks, but generally this is what we have in full generality. So this is, we have a kind of graph with nodes which correspond to devices which produce a classical output, a classical variable. So this is like the output of a random number generator or a measurement performed on some incoming particle. We also have devices corresponding to unobserved node, so like this hidden source which produce state over which we have no control. We have black, so the observed nodes are which produce classical data are in black, the unobserved one in blue, and then we also have observed edges in black which carry this classical data. So for instance, and so what this means is that if I have an arrow coming into some box, it means that at this place, an operation is performed depending on this classical data. Okay? Here can be a measurement setting that's performed depending on that. Here it can be some operation performed in the quantum system depending on this value. And we also, of course, have unobserved edges which carry physical systems between all the devices. Okay, so this is completely general description, and which was introduced by Henson, Lal, and Pusey, and it's useful to make some assumption. First is that we don't allow cycles. Okay, so a box producing an output, but this output cannot be sent in the past of this box to avoid kind of stupid paradox. So the skeleton of this is a graph which is directed because we have directed edge and acyclic, so it's a DAG with nodes which are labeled as observed and unobserved. And in generality, you see that if I have a device like that which produces some classical data, I could also have some quantum system going out of that. So you do a measurement, you have a classical register, but then there is also some quantum system going out. But if you have something like that, I can always view it like this, no? Where I have a system coming here, some operation, so I have like a measurement, and I have the system going out, and then I have some classical data going properly in the thing that outputs this data. Okay, so I can separate in every device. I can separate, if you want, the screen that gives me the reading of the data from the device. Okay, so this is not. We lose no generality by doing that, but if we do that, then we have the property that from every observed node, only black arrows are going out, only observed data, and from unobserved node, only blue arrows are going out, so only hidden systems. And there is nothing fundamental about depicting the graph like that, but it's just more useful because then we will be able to read, to infer some constraint on the probability distribution based on the graph, and it's more it's easier to read this constraint from the graph if it's depicted in that fashion. Okay. So this is the way we are going to represent a kind of arbitrary device impedance scenario where you have these arbitrary devices which are connected together, and this arrow they indicate possible causal connections between different devices. And it's implicit that if you don't have an arrow, then there is no causal connection. Okay, like if I take the Bell DAG, the Bell scenario, there is no arrow between X and B, so it means that this value here cannot influence the output B. So this is this no communication assumption in Bell scenario, and I don't have some common source between the random choice and the proper source of quantum particles. So they are not correlated. This is this freedom of choice assumption. Okay, so if there is no arrow, there is no causal connection. Okay, so this is just a graphical model that describes operationally what we do in the lab. But then we want, of course, to assign probabilities to this classical data. So if we look at classical theory, what does an observer node does? Well, it receives some classical data, some physical system, which in classical theory are just described by classical data. And then it produces some output X. And it does that according to some probability distribution. So I have a probability distribution for the output X, which can depend on all the input classical data. And of course, I don't make any assumption about this probability distribution in a complete device-independent setting, right? I don't know what it is, but there exists some probability distribution. For an observed node, it's the same thing, but what you have is a probability distribution over the output hidden variables. And then you compose these things just by taking the product of the probabilities and summing over the unobserved variables. And if we do that for the Bell DAG, so here I have a box with no input, so it just produces X according to some probability distribution. So this is a random number generator. Same thing here. Here I have an observed node with no inputs, so it just produces some data with some probability distribution. So this is a source of hidden variables. Here, this produces some output A, but this can depend on this classical data and this hidden state. So I have this conditional probability distribution. The same thing here. I take the product of everything. I sum over the hidden variables, and I get the usual notion of Bell locality. And we are more used to write it in terms of the conditional probability, conditional inputs, but it's exactly the same thing. In quantum theory, well, it's similar, but now every observed node is just a POVM acting on the input Hilbert space. And this POVM can depend on the classical data. So this classical data is like a choice of which measurement, which POVM you apply to your system. An observed node, this is just a CPTP map from the input Hilbert space to the output Hilbert space. And again, which CPTP map you apply can depend on the classical data, which is coming here. And then you compose things just with the ordinary composition rule for quantum maps. And so for the Bell DAG, okay, so this is as before. Here we have a CPTP map with no inputs. We just a positive trace one operator. So we just a density matrix over the output Hilbert space. Here we have some POVM with elements indexed by A, and which can depend on the input choice X. Same thing here. I compose things with the usual rules of quantum theory, and I just get the usual quantum description of the Bell experiment. I can also do that for a general probabilistic theory. So I'm not going through this in detail, but one can just directly apply a very useful formalism introduced by Kiribella, D'Ariano, and Perinotti. So you have what they call tests, which generalize the notions of CPTP map or POVMs to other theories. And the only important thing is that this theory should satisfy only one requirement. They should be causal. What it means is that somehow the flow of information should be preserved. So if I have arrow coming in here, there is no information about X that can go backwards in time, if you want. Okay? So in the Bell DAG, this will be equivalent just to ask no signaling. Information of Y here cannot go back to X. Okay? Okay, so now we can draw an arbitrary graph, DAG. We can formally define set of classical quantum or general probability distribution. And now we can ask, given a DAG, is there a gap between the classical and the quantum set? Or maybe we want to classify all DAGs into those for which there is a separation, those which there isn't. To do that, of course, it will be useful to have to derive constraints which are satisfied by classical probability distribution. So that will be the analog of Bell inequalities. In general, these inequalities will not be linear as in the quantum case, but they will be nonlinear function of the classical data. And then we also like to find quantum violation. So it happens that there are already quite a lot of tools which are known on how to derive constraints for general DAG from the field of statistical inference, because these classical models, so when all the variables are classical, this is just called a Bayesian network. And this is something that is studied by people in causal inference, because what you have here is just a bunch of random variables which can causally influence each other. For instance, here some variables may be whether someone has a disease or not. Another variable could be a treatment you can apply, or symptoms, and then could also be hidden unobserved nodes, like maybe whether someone reacts successfully to a treatment can depend on things like is a genetic code, which is things that you don't know. So you have a bunch of variables which can influence each other, some which are observed, some which are not observed. And then you get some data. So you have a probability distribution over the thing you observe. And then you like to know, is this compatible with a certain causal structure? For instance, if I assume that my treatment is responsible for the fact that someone recovered from a disease, is that assumption, this causal assumption, is it compatible with the data I observe? Okay? And so this a basic question you have to answer this. A basic question you have to answer is to find what kind of constraint this causal structure impose on the probability distribution. And so usually people in this field, they look at things a little bit differently that we would do in quantum mechanics. So they have this probability distribution. And if it's not compatible with the causal structure, they would just say, OK, maybe we have to try another causal explanation. While in our device equivalence scenario, we would assume that we know the causal structure. Like in the Bell DAG, we are sure that, for instance, Alice does not communicate to Bob because they're spatially accelerated. So the causal structure is fixed. And if we find that the classical constraints are not satisfied, then we will assume that this is because there is something quantum going on, right? But so the conclusion will be different, but the tools are the same. OK, so we went through the literature, try to find methods people have developed to find constraints in the classical case. There are three main methods which we call the three I's. This is not the standard name, this is the way we call them. So independence, intervention, interruption. I'll say a little bit more about what they are. There is actually a fourth I, which is inflation, which is a technique that was introduced by people in quantum information. So this is a hierarchy of linear programming characterization of the classical set, which was introduced by Wolfie, Speckles, and Fritz, and which was shown by Miguel and Wolfie to be complete. So this is very nice, but it's still useful to rely on other methods, like, because this can be very time-consuming to solve on a quantum computer. Okay, like in the Bell scenario, we know that we have a linear programming characterization of the classical correlations, but it's still useful to have other ways to build the Bell inequalities, right? And we see indeed that this method, they tell us interesting thing about the geometry of these classical quantum and general sets. And another thing is that this method really apply to specific scenarios. Like if I take this DAG and I fix the number, the alphabet of all variables, then I can apply it. But this other method, they work for really families of DAG. They just exploit the causal structure, and you don't need to know anything about the alphabet of this variable. So this can be useful also. OK, so what is the first method, independence? So this is a very standard thing in Bayesian network. So it's best to illustrate it on an example. So consider the following DAG. And now let's ask the question, can x1 and x4 be correlated? Well, here it's easy to see yes, because the value x1 can be passed here to x2. So x2 could actually be just equal to x1. Then this value can be passed to this hidden node, and this could pass this value here. So they could be perfectly correlated. Okay. Now, what happens if this is the thing? If we condition on x2. So let's suppose we observed x2, we know the value, and now let's ask, can x1 and x4 be correlated? Well, now x2 is fixed, so there is a certain number of values for x1 which are compatible for x2. So there is a probability distribution for x1 given x2, but once I fix x2, all the future here is completely fixed, and it's dependent of what value x1 take. So now this path, it's blocked by the fact that I condition on x2. So there is no information from x1 that can go to x4. Okay? So the upper path is blocked. What about the lower path? Well, the lower path in Miller here are what is called a collider. So a situation where you have arrows coming into the node, not going out. So clearly here, this cannot transmit information from one side to the other. So the two paths are blocked. And so if I condition on x2, x1 and x4 are independent. And I can just write this like that. So this is just an equality constraint that is satisfied by the probability distribution. Okay? So every probability distribution that you write for this DAG will satisfy this equality constraint. What happens now if we condition on x2n, let's say, shouldn't be an x3. So we know the path above was blocked. But now if I condition on x3, actually, then I allow again for the possibility of correlation between x1 and x4, because I'm conditioning on an event in the future of x1 and x4. So it could be, for instance, that x3 is equal to 0 if x1 and x4 are equal, or x3 is equal to 1 if they're different. So if I know the value of x3, I know something, I know that x1 and x4 are correlated or anti-correlated, right? So conditioning on a collider open again the path, and so here they can be correlated, right? Okay, so this is a general procedure that you can apply for any DAG. So given a set of nodes, x, y, z, we say that x and y are disseparated by z if all paths from x to y are blocked, where a collider block if this node it's not conditioned upon, so it's not in z, or any of these descendants is not conditioned upon, and this node, so a chain or a fork, block them if they are conditioned upon, like in the previous example. And so by now, given DAG, I can go through all paths between x and y, see if they are all blocked. I say that x and y are disseparated, and in this case, it means that this variable should be independent given z. And there are more clever ways, actually, to derive this independence condition than going systematically through all paths. They're just algorithms which a given graph will output you these independence conditions. So what is known about them? If all nodes are observed, then it's known that this independence condition, they completely characterize the set of classical probability distributions. Okay? So you could define the distribution to be classical in the case where all nodes are observed simply if all these independence conditions are satisfied. If some nodes are not observed, then typically a classical probability distribution will satisfy additional constraints, and an example is in the Bell DAG. So if I do this kind of trick, in the Bell DAG, I find that the conditional independence assumptions are these ones, which are just the usual no-standing constraints, but we know that there are Bell inequalities which are additional constraints. Okay, so what Henson, and Pusey showed is that this conditional independence condition, they also hold in the quantum case and in the general probabilistic case. And okay, so they formalize this precisely, but intuitively, it's not very difficult to be convinced about that, because it's just about how information can flow, and whether some nodes are quantum or classical, it really doesn't matter. If they're in that configuration, they can propagate information. If they are in that one, they can't, right? And so it's intuitive that the same kind of result should hold, and indeed, this is the case. Okay, so here, this is an example of constraints we can derive for the classical set, which actually also hold in the quantum set and in the general set. So these are constraints for which there is no quantum or general probabilistic theory separation. Still, this is quite useful, actually, because in this paper, Henson and Pusey, they give a sufficient condition which, if it's satisfied, a sufficient condition for all these equality constraints to characterize completely the classical set. Okay, so given a DAG, you can run a test. If the test passes, you know that there are no additional constraints than these ones. If the test fails, maybe there are, maybe there aren't, you know. But if the test passes, you know that this completely characterizes the probability distribution, but these constraints are also valid for Q and G, and thus there is no quantum advantage for that DAG. And so they use this algorithm on all DAGs with less than 7 nodes, and so they were able to discard a lot of them, which are actually boring. Okay, there will never be quantum advantage. If you see the first time when there is an interesting DAG, it's for 4 nodes. So there is, out of the 420 possible DAGs with 4 nodes, there is a single one for which this condition is not satisfied, which is just potentially interesting. Maybe there is a quantum advantage. I will come back to that later. Okay, so now if I look at the situation in Bell scenario, okay, so I have found equality constraints which are valid for CQG, and which turn out to be the no-singling constraint. So based on this, it would be natural to conjecture that these equality constraints, they completely characterize the linear space in which these sets live. Okay? Actually, it's not the case. So it's the case in the Bell scenario, but for general DAG, it's not the case. In general, there will be additional equality constraints in addition to the one that you can derive with this separation technique. And to see this, one has to consider a second method, which we call the intervention method. So again, it's simpler to see an example. So consider this DAG, okay, which is characterized by some probability distribution over the observed variables. So what I can do here is what is called an intervention. Intervention is I take some node and I fix the value of that node. Okay? Suppose I could physically go there and replace this by a box that certainly produces some output x3, and the same thing here. So if I do that, then it's clear that here I remove that edge, okay, because I fix the value of x3. And then I can look at the probability distribution of the nodes on which I didn't intervene, so x2 and x4, and this will be a conditional probability distribution, x2, x4, given x1, x3, which will take this specific form, okay, because x2 can depend on some hidden variable lambda and on x1, x4 can depend on hidden variable lambda and x3. Then I sum over the hidden variable and I get this probability distribution. I can also make an intervention on x2, fix the value of x2. If I fix it and discard x4, so then I get this simple DAG, characterized now by this probability distribution, and it's clear that the full probability distribution is just the product of these two. Okay, it's like what happened if I fix x1, x3 to some value here, and here x2 and x1 to some value, and it's clear that this factorizes like that. So this factorizes like that, with an interesting property, which is if I look at this guy here, if I sum over x4, then the dependence on x3 disappears, because there is only x4 that depends on x3. And if I sum over x2, then the dependence on x1 disappears. So now I see I have not much time, so I will not go to the detail, but from this property, this simple expression from my probability distribution, I can recover the usual conditional dependence constraint that could have been derived with this separation. But you can also derive new equality constraints, which involve some sum, and so which are not of this simple type we've seen before, and which are not implied by this separation. Okay, so it's a technique here which we can also generalize to arbitrary DAGs. So there is two guys which have proposed an algorithm to systematically derive equalities using this kind of intervention, and this will output all the conditional independence constraints you can get through this operation, but in addition, some additional ones, like this one. And it was shown by Evans 2 years ago that all these equality constraints that are output by this algorithm, they are complete for C in the sense that the classical region is a full dimensional subset of the probability distribution satisfying these equality constraints. So there are no more equality constraints that are valid, no more independent equality constraints that are valid from the classical set. Okay. And so what we have shown is that this equality constraint actually also hold in the quantum case and in the general probabilistic theory case. And again, I mean, it's not, so in this example, it's not difficult why it's old. It's because this property here also old, of course, in the quantum case. It's just about what if I trace one party, what kind of causal connection remain, but it's really independent of whether the underlying model is classical quantum. So you can formally show that this also holds in generality. So then this solves a problem of trying to find the generalization of the no-singing condition. Okay? So I know that these equality constraints are satisfied by all three sets, and I know that the classical set, which is a smaller one, it's full dimensional in that subspace. So it means that all these sets, they live in this hyperplane defined by these constraints. And so this Tian and Pearl algorithm gives me a way to derive the generalization of no-singing condition for arbitrary DAGs. This is useful because well, when you work with low locality, you know it's very useful usually to work in the no-singing subspace, but then you have a way to define that subspace for an arbitrary DAG. Okay, so now based on this picture, one may conjecture that the set of generalized probabilistic theoretic correlations is simply described by these equality constraints. This is what happened, in the Bell scenario. The set G is the most general set compatible with the no signaling condition. This kind of tautology. But actually, so this is not the case. So this can be shown using another technique. So I will not go into the detail, but Evans has shown a few years ago that it's possible to derive inequality constraints which are satisfied by classical correlation. And again, we can show that they are also satisfied in the quantum and the general case. Okay? So contrarily to the picture here in Bell scenario, for a general DAG, the set compatible with the more general causal theories will be a stricter subset of the full probability space. Okay. So okay, so I don't explain you how it works, but okay, this can be done. And if you apply in particular to a scenario which is known in the statistical literature as the instrumental scenario, so it's something that comes again and again because it has some application actually. So this is called the instrumental scenario, and in this case, you can show that C and G are there are no equality constraints that hold. Okay, so if I write a distribution P of x1, x2, x3. It will be determined by d to the power 3 parameters, -1 for normalization, where d is the alphabet of these guys. But using this interruption method introduced by Evans, you can show that CQG will satisfy all one inequality constraint, which is this one. And these are known as the instrumental inequalities in statistical inference literature. Okay, so this is kind of the summary. So we have these three methods, which have been derived in a purely classical setting, but actually they all hold for quantum and general theories. So it's kind of funny that actually the only thing that really matters are the causal connection between the devices to derive this kind of thing, but not whether the devices behave according to classical quantum or general theory. And what is nice, I think, is that this intervention method gives you the full set of equality constraints for these sets, and so it generalizes the no-singing conditions. So now an open question. So we know we have the most general characterization of the equality constraints of these three sets. Now it would be nice to know, so an open question will be what is the full characterization of the inequality constraints. We know that there are some inequality constraints. Some of them can be derived using this interpolation technique, but are there more that hold generically? So this is some open question. Another thing that one could do maybe is improve this classification done by Henson, and Pusey that I showed you before, where you discard boring DAGs. One could maybe improve that using this additional understanding we have of these sets, but this is something we have not done yet. Okay, so speaking about this Henson-Pusey result, so I told you they have identified the simplest possible DAG. So let's look at this DAG. It happens that it is this instrumental DAG, okay? Instrumental scenario. So the question is, so we know here that there are no actually equality constraints, okay? And now we like to know, are there still constraints that separate the classical from the quantum region? Is there a distinction between quantum and classical correlation in this scenario? So how is it defined, this scenario? Well, the classical correlations, you know, we can read it like that, of course. So you have this source, which sends hidden variable lambda. So the output A can depend on X and lambda. The output B here can depend on A and lambda. Then you sum over the hidden variable, so you have this characterization. And in quantum case, you have something similar. So this source now produces some bipartite entangled state. Here do some measurements with outcome A, which can depend on X, and here do some measurement with outcome B, and this choice of measurement can depend on A. Okay, so it's clear that this scenario actually it's very much related to the Bell scenario, because you know, I can just view this instrumental scenario as a Bell scenario where instead of determining the choice of measurement setting performed at B by some independent random choice Y, what I do is that I use the output of Alice to determine what measurement is done here. Okay? So it's kind of a relaxation of the Bell scenario where this is not chosen randomly, but is determined by the output of B. Okay? And then you can ask, if I do that, can I still observe a separation between the classical and the quantum case? So people have considered many relaxations of this Bell scenario, like what happens if you have very weak input randomness, or if you allow communication between the two devices. But to my knowledge, nobody had looked at this question, what happens if you use the output of one device to select the input on the other device. Actually, it's not difficult to see that this instrumental scenario can just be seen as a post-selection of the Bell scenario, where you run a standard Bell scenario, and then you just discard all the data when Y was different than A. Okay? And you keep all probabilities when Y was equal to A. This will formally be equivalent to doing that. Okay? So this is just a post-selection, but you know that when you do post-selection, usually you increase the power of the theory, like this is the detection loophole. No? If you throw away some data, then things which naively you could think are quantum becomes start to admit a classical description. So by doing this post-selection, by throwing part of the data, it could be that the same thing happened here, and that suddenly everything always become explainable by classical description. So let's try to look whether this happens or not. So let's take the simplest possible case where all these variables can take binary values. Okay? So this is a kind of post-selection of CHSH. Okay? CHSH, every variable takes binary values, and now I do a post-selection of that. I throw all the data when Y was not equal to A. So the Bell scenario is a polytope. This post-selection will also be a polytope, which I can compute. And if you do that, you will find that there is only one facet, which is this instrumental inequality, which we already know. But we also know, because we've shown that before, that it's not violated by quantum theory or by a generalized probabilistic theory. Okay, so no violation. So then, of course, what you do, you just go to the next case, where now I keep A and B to be binary, but I take 3 values for X. Now, if you solve the polytope, you find a new inequality, which is this one, which actually was already derived in the statistical inference literature by Bonnet. And now if you take this inequality, so it's not one of these instrumental inequalities, it's a new one, and you can show that it can be violated by quantum mechanics. So Just assume that the source here produces some maximally entangled state, so a phi plus state. And here on Alice side, we have 3 choice of measurements because x can take 3 values. The usual CHSH measurements plus another one. And on Bob's side here, you have 2 measurements, whether, if a equal to 0, you apply this one. If a equal 1, you apply this one. So again, these are just the CHSH measurements. And if you compute the probabilities, you will see that they violate this inequality, so you get this value. And if you add PR boxes here, you can even go higher. Okay? So you have some quantum violation. But okay, there is not really anything fundamental about this, right? It's just the same non-local resource as always that we use. It's just that you have shown that some specific non-local correlation involving 3 inputs are quite robust in the sense that even if you discard some of the data, from the remaining data, you can still conclude that these correlations were non-classical. Okay, so I would say this is just an observation, but apparently this observation is sufficient to get you in nature physics, because when I prepared this talk, yesterday actually, I Googled instrumental scenario, and then I found this paper, which was published Monday actually, so 2 days ago, where they point this out, and they also do an experiment where they show that this correlation can produce them. Okay, so it's a kind of variant of the standard CHSH experiment. So as I said, there is nothing very fundamental about this, but there is actually some nice observation, which actually was not noticed in this paper, which is, if you had told me what is the minimum. So you know that if you have a device-independent experiment, you need some input randomness to test things and to prove that you have some quantum correlation. And if you have asked me what is the minimal alphabet size of the input randomness you need, I would have said this is CHSH, so 2 bits, 1 bit for Alice, 1 bit for Bob. But here we have a kind of device-independent scenario where we only need 1 trait of input randomness. Okay? By doing this trick, of using the randomness produced by Alice to determine the random choice at Bob's side, we can do away with a little bit of randomness. So maybe actually this is maybe related to this paper by Schill Miller on local randomness, where they show that if you do a kind of non-local experiment like that, the output of Alice is random even from the point of view of Bob. So maybe something like that here is used. Okay, okay, so this is a nice observation. And then you say, okay, maybe this can improve the efficiency of randomness generation protocols. From this experiment, I should be able to certify randomness, but I will consume maybe less input randomness than using a standard CHSH test. So you can actually certify the amount of randomness that's put it here in the scenario just by using this mapping between the two through the post selection. You can use, like you can see that the NPI hierarchy, for instance, will map to this scenario. And so you can, as a function of this instrumental inequality, you can plot, for instance, the guessing probability associated to the output of Alice and Bob. So this is just a measure of the randomness of the outputs. So this is this curve here. And you can also plot the same thing for the CHSH inequality by normalizing the inequalities so that they're somewhat similar, and it's exactly the same thing. So you can certify the same amount of randomness as the CHSH inequality, but using maybe a little bit less input randomness. So this is not yet a protocol, so I don't know if when you do a protocol, it gives some improvement, because it may be that this inequality, is less robust to statistical fluctuation. So even though at each run you use less randomness, maybe you have to use more runs in total to certify the same amount. But okay, so this is something to look at. Okay, when you do this, so this kind of thing, when you've written the program to this curve, you can also look at other kind of configuration. So here, this is the guessing probability when I use input 0 on Alice's side. I can also look at the local probability of Alice output when I use other inputs. And if you plot the guessing probability of Alice output when you use x equal 2, you get, this is 1 here everywhere. Okay? So no randomness. So this is strange because in this experiment, the output of Alice is not determined. Okay? But if I run this NPI hierarchy, I find 1. So maybe this tells me that there is another way to get this violation, another quantum strategy, where there is no randomness at all produced on any side. And so what you can try simply is just replace this observable by just a trivial observable, okay? Just the identity. So it means here that when you put x equal 2, x equal 0, you measure sigma z. X equal 1, you measure sigma x. X equal 2, you just output 0. And if you do that, you get the same violation, okay? But this can be understood, as a kind of trivial mapping of the CHSH correlation to a situation with 3 inputs. Okay, if I forget about this third input, so I'm just looking at CHSH correlation with 2 measurements on each side, but I need to have 3 inputs here to use them in this inequality, in this scenario. So I just trivially define that when I get the third input, the output will always be 0. Okay. And then this works. And we can understand that, so this is kind of a bit strange maybe, but we can understand this better by looking at this inequality. So this inequality is defined for probabilities in the instrumental scenario, but I can view them as probability in the standard non-local scenario before post-selection, right? And so this is the inequality. So this inequality rewritten in the standard non-local scenario, right? Because this, for instance, if A equals 0, B is equal to 0, but if A equals 0, Y is equal to 0. So I get this. If A is equal to 1, B is equal to 1. But if A is equal to 1, Y is equal to 1. So I have this. So this term becomes this. Okay. Same thing for the other one. And then I can just rewrite this inequality by using the normalization condition or string condition. I can rewrite it like that. CHSH minus something plus 3/2. So this is completely general. And it already tells us something, because this guy, of course, it's always negative. So a bound on the CHSH inequality gives me a bound on this inequality, and actually the bound on the CHSH inequality is just directly related to these bounds. Okay. But the more interesting thing is that if I do this trivial mapping of the CHSH correlation to 3 inputs, then, as I said, this box always outputs A equals 0 when x equals 2, so this probability is always 0, and then now I have a one-to-one correspondence between the CHSH value and this inequality. So I violate this inequality only if I violate the CHSH inequality. Okay, so in this Nature Physics paper, for instance, that was even not necessary to do an experiment. It has already been done. It's just the CHSH inequality, but you just interpret it differently by throwing some of the data. So another way to say this is that this gives you also a new way to test the CHSH inequality. So instead of using 2 input bits to determine inputs 0, 0, 0, 1, 1, 1, and gather the correlations, you can test the CHSH inequality by just having a random number generator producing one trait. Then if the value is 0, 1, you input that in your measurement device on any side, take the output and put it here. And if the value of the input generator is 2, then you can directly input y equals 0 here. Okay, so if I put 2, a is equal to 0, but of course I don't need to do this kind of trivial wiring. I can just directly, if the value is 2, I can just directly input here y equals 0. Okay, so it shows you that you can test the CHSH inequality in a situation where you need to look at less data. And maybe this again can improve the statistical testing. Maybe to reach the same p-value, you need less measurement runs, or maybe, okay, I don't know. This is something we have to look at. Okay, so this is, I think it's a funny observation. So people have known the CHSH inequality for a long time, but somehow it was missed that you can test it in a simpler way. And now, of course, the user-open question is, can you find a device-independent scenario where you only need 1 bit of input randomness to prove that there is some quantum advantage? Okay, so this, I don't know. I can finish here.
Thanks, Stefano. Are there any quick questions? Okay. So do you think there's lower bound on how many, is there a trivial lower bound on how many bits you could need in order to have a violation? Like we went from like 2 bits to a treat.
How many lower bound on the input bits?
Yes.
Okay, we know we can do it with a treat. So the open question, can you do it with a bit? We don't know. But you need something, so you need at least 1 bit.
So yeah, but do you think this should be 1 bit, or I don't see what is very fundamental about log 3 somehow. I mean.
No, I don't know. So perhaps you can, but I have no idea if it's possible. Yeah.
All right, so let's thank Stefano again.